Hello, welcome to Advanced Composites. Today is the last day of this course, and today we will be continuing our discussion on buckling of composite plates. And in this case, we will have a composite plate which will be simply supported on all four sides, but it will be loaded bidirectionally. So, it will experience load in the x direction as well as in the y direction. Now, these kinds of loads can be generated in two types of situations. Either we are actually putting external load in both the directions, so the external force is being applied in both the directions, or these forces could also be developed. That suppose I have a plate which is being compressed in the x direction by some value n, and if I am constraining the v displacement in the y direction, then the plate naturally will try to have an expansion. As it is getting compressed in the x direction, it will try to expand in the y direction due to Poisson effect. But if I am putting a constraint in the y direction so that the plate cannot expand, then it will generate Ny automatically, and because of that value of Ny, the plate will get compressed in bidirectionally, and that will generate some different type of buckling pattern. So, in either of these cases, we can solve the problem of plate buckling, especially for simple geometries such as rectangular plates which are simply supported or clamped, or in these kind of situations. So, we will look at plate under bidirectional compression. So, this is x, this is y, that is my plate. This dimension is b, this dimension is a. I am having the external load. So, it is uniformly getting compressed in the x direction, and here it is simple support. So, plate is simply supported on all four sides, but once again we will explicitly state what do these simple support mean. So, it is getting compressed in this direction, and also it is getting compressed in the other direction. So, let us say this is n in the x direction, and the compression force resultant in the vertical direction or y direction is some constant k times n. Now, we will look at the boundary conditions. So, when this kind of loading will happen, when the v displacement is being constrained. So, if I double n, the value of Ny in the other direction will also get doubled. So, this is the type of simulation situation we are trying to simulate. So, BCs are, so let us call these edges. So, this is edge 1, edge 2, edge 3, edge 4. So, on edge 1 we have W equals 0, Mx equals 0, U equals 0. On edge 2, W equals 0, Mx equals 0, and Nx is equal to N, Nx plus. On edge 3, W equals 0, My equals 0, and Ny equals k times n, and it is actually negative, both are compression. And on fourth W, so these are all mid plane displacements. So W equals 0, My plus equals 0, and V equals 0. So once again we are interested in understanding out of plane behavior. So we solve only the third equation. Why is that the case? Because we again assume that plate is symmetric and it is also orthotropic. So because of symmetry, B is equal to 0, B matrix, and because of orthotropy, D16 is equal to D26 is 0. Okay. So we assume a solution. So again we are going to solve this problem in an exact way. So we assume that the solution is W naught sin m pi x over a times sin n pi y over b. So this is equal to the mid plane deflection in the z direction. Okay. So then we see that W naught xy is equal to 0 at x is equal to 0 and a, and y is equal to 0 and b. So kinematic BCs are satisfied. Then we have to ensure that moment related boundary conditions on the 4 simple supported edges are also 0. So mx is equal to, for this plate, d11 del 2 W naught over del x square plus d12 del 2 W naught over del y square, and this entire thing is negative, and my is equal to minus d12 del 2 W naught over del x square plus d22 del 2 W naught over del y square. Okay. So this gives us minus d11 m pi over a whole square plus d12 n pi over b whole square sin m pi x over a sin n pi y over b, and then of course there is a W naught here and minus, and this is minus W naught d12 this square plus d22, the other parameter in brackets is squared, times again sin m pi x over a sin n pi y over b. So if I plug in the values of x and y for different edges, I see that mx is equal to 0 at x is equal to 0 and a, and my is equal to 0 at at y equals 0 and b. So all BCs are satisfied. Out of plane BCs are satisfied. Okay. So the last thing is that we satisfy the PDE, partial differential equation. And which partial differential equation? Which is the third. Okay. So now here we have both Nx and ny, and we know that nx is constant in the entire plate because it's uniformly loaded. So, nx does not change with respect to x and y, and ny is also constant, and that is equal to k, and both of them are negative. Okay. So, and then of course, nxy is 0. So, our overall differential equation is nx del 2 w over del x square plus ny del 2 w over del y square plus del 2 mx over del x square plus 2 del 2 mxy over del x del y plus del 2 my over del y square is equal to 0. Now, we have already, so this gives us minus n del 2 w naught. So, this is all mid-plane displacement. So, del 2 w naught with respect to x minus k times n del 2 w naught over del y square minus, so I am going to take minus out and everything inside the will be positive. So, this becomes d11 del 4 w naught over del x 4 plus 2 d12 plus 2 d66 del 4 w naught over del x square del y square plus d22 del 4 w naught over del y 4 equals 0. Okay. So, this is the differential equation, and now what I do is substitute w naught x y as what? W naught sine m pi over a times x sine n pi y over b. So, I get minus n m pi over a whole square minus k n n pi over b whole square plus d11 m pi over a to the power of 4 plus 2 d12 plus 2 d66 m n over a b pi square, entire thing is squared, plus do d22 n pi over b whole to the power of 4 into w naught sine m pi x over a sine n pi y over b is equal to 0. So, again, for this equation to be true, which means right and left side should be 0. So, suppose I have this entire thing in green and this is w naught. So, for this equation to hold, either w naught should be 0 or this entire expression in green should be 0. So, that is my pre-buckling solution, and this is buckling solution. Pre-buckling solution and buckling solution. Okay. So, we look at the buckling solution. So, what do we get? So, if I have to solve for n, then what I get is pi square over a square times d11 m4 plus 2 d12 plus 2 d66 m square n square r square plus d22 n4 r4 divided by m square plus n square r square times k, okay, where r is equal to b is equal to a over r or r equals a over b. Okay. So, that is the aspect ratio of the plate. So, this is how I can calculate the value of n at which it is going to fail, not fail, it is going to buckle. Now, one or two important things. One is this parameter k. Okay. So, as k goes up, assuming k is more than 0, which means the compression load on the y axis also is increasing. So, as k goes up, n decreases and vice versa. Okay. Second, if k is negative, which means that I am pressing the plate like this, but on these ends I am not pressing the plate, but I am pulling it. Okay. If k is negative, which means in y direction, so which means that ny is tensile. So, what does that mean? That n goes up, n goes up. So, plate tends to become more stable. So, this is something important to understand. Okay. And the mode shape depends on m and n, and which in turn is related to aspect ratio of the plate, So, that is all I wanted to discuss for today, and this concludes our discussion on buckling. Tomorrow we will introduce a new topic, and we will switch gears starting next week, and we will start talking about short fiber composites. So, that is what I plan to do today, and I look forward to seeing all of you next week as well. Thank you.